Welcome to example 16 in our functions and graphs topic. If you haven't watched example 15, do that first of all, just a wee introduction to why we might want to find the nature of a stationary point using the second derivative and how we do that. So straight on to example 16, it says find your stationary points and their nature given this cubic function x cubed plus 3x squared. So the first thing I want to do is to investigate where or for which values of x the stationary points might occur. So if our function f of x is x cubed plus 3x squared, then the first derivative, f dash x, is 3x squared plus 6x. Why are we doing that? Because we can state that stationary points exist when the first derivative is equal to 0, when the gradient is 0. We've deduced that the first derivative here is 3x squared plus 6x, and if we equate that to 0 for this function, that will give us our stationary points. We seem to be able to factorise that. We've got a common factor of 3x, which leaves us x plus 2 is equal to 0. So we can say that either the first factor equals 0 or the second factor is equal to 0, and from that we can solve for x equals 0 or x equals negative 2. It says find a stationary point, so I'm going to find the y coordinates next. You do it in a different order, but we'll do it this way. So we've got two values of x and we're going to substitute them into the original function. So for f of negative 2, that's going to be negative 2 cubed plus 3 times negative 2 squared. Negative 2 cubed is negative 8 plus 3 times positive 4. And that's going to give me negative 8 plus 12 is positive 4. And for f of 0, that's slightly easier to work out. It's just going to be 0. In other words, we can say that our turning points, or stationary points, because we don't know if they're actually turning it, stationary points at the moment are negative 2, 4 and 0, 0. Okay, so now we want to try and find the nature of these points, and you could use a nature table, but the whole point of this example is we're going to use the second derivative. And for basic polynomial functions, quadratic, cubic, quartic functions, it is quite a quick way to do it. So what did we do? We're going to check the second derivative. So we can say that from our first derivative above, if we differentiate 3x squared plus 6x, we're going to get 6x plus 6. Agreed? So that's our function of our second derivative. Okay. So what we need to do now is check the value of the second derivative for each value of x where our stationary points are negative 2 and 0. So we can say at x equals negative 2, if we put negative 2 into our second derivative, we're going to get 6 times negative 2 plus 6, which is negative 12 plus 6, which is negative 6. And negative 6 is obviously a negative value. What does that mean? Negative second derivative means that it is concave down, and concave down means a maximum turning point. Okay. Concave down means the gradient is getting low, it's becoming more negative all the time. Okay. And if we check the other value, x equals 0, and we put that into our second derivative, we get 6 times 0 plus 6, which is positive 6. So because that's positive, we can say that it's a minimum turning point. Because if the second derivative is positive at that point, then it's part of a situation where the gradient's getting bigger. concave up, which is a minimum turning point. So we've got the nature quite quickly from these two calculations, and we can conclude by saying that we've discovered that there are, what we worked out, x equals -2. We've got a maximum turning point at -2, 4, and we've got a minimum turning point at 0, 0. And the point being, we're about to feed this into our graph sketching, so it's one part of the process that we're going to do. It's a standalone skill that you can use anytime you're investigating stationary points as well. Okay, hope that's been helpful. We're going to go on and have a look at sketching graphs of rational functions, which is a lot of fun. So join us for example 17. Okay.